Hello everyone. In this lesson we will look at how to apply Bayes' theorem to the Monty Hall problem. You may recall from the beginning of the term that we studied the Monty Hall problem. It's a problem that comes from an old game show called Let's Make a Deal, and it's named after the show's original host, Monty Hall, pictured there on the right. If you recall, the problem involves a contestant trying to win a brand new car. There are 3 doors on the stage, and the car has been placed behind one of the 3 doors at random. In order to win the car, the contestant simply has to pick the door that conceals the car. Let's suppose that you're the contestant and you choose door number 3. At this point, Monty will open a door. Your choice was not constrained. You could have chosen any door you wanted to. But after you make your choice, Monty will open a door. He does not open the door you chose, and he does not open the door that reveals the car. So let's suppose that Monty opens door number 2, revealing that behind door number 2 is a whole lot of nothing. At this point, Monty will give you a choice. Do you want to stick with your original door, door 3? Would you like to switch over to door number 1? The question is really, do you have an incentive to change? Or in other words, does your probability of winning the car go up if you were to change to door number 1? Intuitively, the answer is that, well, look, when you chose door number 3, you had a 1/3 chance of picking the winning door. You also had a 2/3 chance of not. There's a 2/3 chance that the car is behind door 1 or door 2. When Monty opens door number 2, it feels like the odds get reset. Now, the car is either behind door number 1 or door number 3, and it feels like it could be either place, and the odds are split evenly. So it seems like there's a 50-50 chance that you've got the winning door, and you have no incentive to change. As intuitive as this answer seems, it is incorrect. The correct answer is that yes, when you chose door number 3, you had a 1/3 chance of picking the winning door, and a 2/3 chance that the car was behind one of the other doors. When Monty opens door number 2, that 2/3 chance gets pushed all the way over to door number 1. Now, door number 1 has a 2/3 chance of having the winning car behind it. So in fact, you have a huge incentive to change if you want to win the car. Your probability of winning doubles. We're going to apply Bayes' theorem to this problem. So as a refresher, Bayes' theorem is a definition of conditional probability, and for this problem we can use the simplified form of Bayes' theorem, which is right here. It says that the probability of a hypothesis H given an item of evidence E equals this ratio, the probability of the hypothesis times the probability of the evidence given the hypothesis divided by the total probability of the evidence. This expression on the left is called the posterior probability of the hypothesis. It's a measure of the probability of the hypothesis after the evidence has rolled in, and it represents the impact of the evidence on the probability of the hypothesis. That's the probability that we want. On the right-hand side of the equation are the priors, or the prior probabilities. These are the probabilities we have. Before we move on to applying Bayes' theorem to the Monty Hall problem, I do want to remind you about the difference between the simplified version of Bayes' theorem and the more complicated version of Bayes' theorem. They're both equivalent. The only difference is the denominator of the ratio on the right. So where we have the probability of E, the complicated version would have this probability weighted average at the bottom. So the probability of E equals the sum of these weighted probabilities, the probability of the evidence given the hypothesis weighted by the probability of the hypothesis, plus the probability of the evidence given not H, or the probability of the evidence given that the hypothesis is false, weighted by the probability of not H. Those tildes in front of the H's are negations or denials. So tilde H is just read not H. And sometimes we need to use the complicated formula in order to solve the problem. In this case, we can use the simplified version. So let's take a look at the problem. We're going to apply this twice, actually. We're going to go through it twice with two different hypotheses. So let's consider the first hypothesis, H1. We'll call it H1, and it's the probability that the car is behind door 3. That's your door. And the evidence that we're interested in is provided by Monty opening door number 2. So here's Bayes' theorem with H1 in place of simple H. So the probability of H1 given E is the probability of H1 times the probability of E given H1 divided by the probability of E. We're going to keep these doors up here to help us walk through these prior probabilities. So we have up here door 1, door 2, and door 3. And let's keep in mind that you chose door number 3. So if we look at this hypothesis, the car is behind door number 3, what is the prior probability of that hypothesis prior to Monty opening any doors? Pretty intuitively, the probability is 1/3. There's a 1/3 chance that the car is behind your door. Now, what's the probability of the evidence given the hypothesis? That is to say, what's the probability that Monty will open door number 2 if the car is behind door 3? Well, if the car is behind door 3 and you chose door 3, Monty could equally open 1 or 2. So the odds are even that Monty will open door 1 or door 2, and that means that the probability of E given H1 is 1/2. Finally, what's the total probability of the evidence? This is actually a fairly simple problem, a simple question. Anytime a contestant chooses a door, there remain 2 other unopened doors. And given that the car is placed randomly behind the 3 doors, that means that Monty has to open one of the other 2 open doors, and the odds will always be even between them. So actually the total, once a door has been selected, and you selected door 3, the probability that Monty will open either of the other doors is actually 1/2. It's the total probability of the evidence. So this one turns out to be fairly easy to solve. 1/3 times 1/2 divided by 1/2, we know that those cancel, equals 1/3. So what I want to point out here is that this is our posterior probability of the hypothesis, right? And this was our prior probability of the hypothesis. Okay? So what's happened is when Monty opened door number 2, he didn't do anything that makes a difference to the probability of H1. The probability that the door is behind door 3 was 1/3 before Monty opened door 2, and it stays 1/3 after Monty opens door 2. So let's take a look at another pass at this problem. Let's examine H2. The car is behind door 1. Here we have the hypothesis H2 plugged in to Bayes' theorem. And here, once again, we have our 3 unopened doors: door 1, door 2, and door 3. This is your door, door 3. So, how are we going to solve Bayes' theorem? Let's examine each of these priors one at a time. What is the prior probability that the car is behind door number 1? Well, the car could have been placed anywhere. And so we know that the probability that the car is behind door 1 at the outset is 1/3. Now for the second prior, what's the probability of the evidence given that hypothesis? What's the probability that Monty will open door number 2 given or assuming the car is behind door 1? Well, Monty's not going to open door 3 because you chose it. Monty's not going to open door 1 because that's where the car is, we're assuming. So Monty has to open door 2. So the probability that Monty will open door 2 if the car is behind door 1 is 100%. Finally, in the denominator, the total probability of the evidence, it hasn't changed. The probability of the evidence, independent of the hypothesis, is still 1/2. Once you've chosen a door, the other 2 remaining doors have a 50-50 chance of being opened by Monty. So 1/3 times 1 is 1/3. And then we take 1/2 and carry it down to the denominator. Now, if you remember, to divide by 1/2 is to multiply by the inverse. So 1/3 divided by 1/2 is the same as 1/3 times 2/1, and that is 2/3. If we look up here, we see that the prior probability of our hypothesis H2 is 1/3. If we look down here, the posterior probability of our hypothesis is 2/3. So the probability of H2 doubles after Monty opens door 2. To summarize, the probability that the car is behind door 3, your door, given that Monty opens door 2, is 1/3. That was the same as the prior probability. The probability that the car is behind door 1, given that Monty opens door 2, is 2/3. That's double its prior probability. And since the probability of H2 is greater than the probability of H1, you should switch.